Continuing from where we left off, finding a point estimate and margin of error from a confidence interval. Technology and journal articles often express a confidence interval in a format such as 10.0 to 30.0. The sample mean X bar is the value halfway between those limits, and the margin of error E is 1/2 the difference between those limits. So the point estimate of mu is X bar, which is equal to the upper confidence limit plus the lower confidence limit divided by 2. And the margin of error E is equal to the upper confidence limit minus the lower confidence limit divided by 2. For example, the confidence interval 10.0 to 30.0 yields X bar equals 20 and E equals 10. In some cases, confidence intervals might be among the different tools used to describe, explore, or compare data sets, as in the following example. The figure below shows graphs of confidence interval estimates of the mean cotinine level in each of 3 samples: people who smoke, people who don't smoke but are exposed to tobacco smoke at home or work, and people who don't smoke and are not exposed to smoke. We see that the confidence intervals for non-smokers overlap. It is possible that they have the same mean cotinine level. It is helpful to compare confidence levels or their graphs, but such comparisons should not be used for making formal and final conclusions about equality of means. If we want to collect a sample to be used for estimating a population mean mu, how many sample values do we need? When determining the sample size needed to estimate a population mean, we must have an estimated or known value of the population standard deviation sigma, so we can use the formula below. The sample must be a simple random sample. The required sample size is found by the formula n equals z sub alpha over 2 times sigma all over E quantity squared. Note that we are using z sub alpha over 2 here while we have used t for other calculations regarding estimating population means. If the computed sample size n is not a whole number, round the value of n up to the next larger whole number. Note that, as with other calculations of sample size, this formula does not depend on the size of the population. The formula given on the previous slide requires a known value for the population standard deviation, sigma, but in reality, it is usually unknown. When determining a required sample size, not constructing a confidence interval, here are some ways to work around the value of sigma. Use the range rule of thumb to estimate the standard deviation as follows. Sigma equals the range divided by 4, where the range is determined by sample data. Start the sample collection process without knowing sigma, and using the first several values, calculate the sample standard deviation S and use it in place of sigma. The estimated value of sigma can then be improved and the required sample size adjusted as you collect more sample data. Estimate the value of sigma by using the results of some earlier study. In addition, we can sometimes be creative in our use of other known results. When determining the sample size n, any errors should always be conservative in the sense that they make the sample size too large instead of too small. Assume that we want to estimate the mean IQ score for the population of statistics students. How many statistics students must be randomly selected for IQ tests if we want 95% confidence that the sample mean is within 3 IQ points of the population mean? For a 95% confidence interval, we have alpha equals 0.05. So z sub alpha over 2 equals 1.96. Because we want the sample mean to be within 3 IQ points of mu, the margin of error is E equals 3. Also, we can assume that sigma equals 15, as Wechsler IQ tests are designed to have a standard deviation of 15. Using the formula we saw before, we get n equals z sub alpha over 2 times sigma over E quantity squared, which is 1.96 times 15 over 3 quantity squared, which is 96.04. We round the value of n we get from the formula up to 97, the next larger whole number. With the simple random sample of only 97 students, we will be 95% confident that the sample mean X bar is within 3 IQ points of the true population mean. In the real world of professional statisticians and professional journals and reports, it is extremely rare that we want to estimate an unknown value of a population mean mu, but we somehow know the value of the population standard deviation sigma. If we do somehow know the value of sigma, the confidence interval is constructed using the standard normal distribution instead of the t distribution. So the same procedure from part 1 can be used with this margin of error. The margin of error E equals z sub alpha over 2 times sigma over the square root of n, used with a known sigma. Use the same 15 birth weights of girls given in our previous example for which n equals 15 and x bar equals 30.9 hectograms. Construct a 95% confidence interval estimate of the mean birth weight of all girls by assuming that sigma is known to be 2.9 hectograms. With a 95% confidence interval, we have z sub alpha over 2 equals 1.96. Using sigma equals 2.9 hectograms and n equals 15, we find the value of the margin of error E. E equals z sub alpha over 2 times sigma over n, the square root of n, which is 1.96, times 2.9 over the square root of 15, which is 1.46760. With x bar equals 30.9 and E equals 1.46760, we find the 95% confidence interval as x bar minus E is less than mu, which is less than x bar plus E, which gives us 30.9 minus 1.46760 is less than mu is less than 30.9 plus 1.46760. So 29.4 hectograms is less than mu is less than 32.4 hectograms. When constructing a confidence interval estimate of the population mean mu, it is important to use the correct distribution. The table below summarizes the key points to consider. Conditions. If sigma is not known and normally distributed population, or sigma is not known and n is greater than 30, we use the t distribution. If sigma is known and normally distributed, or and the population is normally distributed, or sigma is known and n is greater than 30, in reality, sigma is rarely known, we use the normal z distribution. And if the population is not normally distributed and n is less than or equal to 30, we use the bootstrapping method, which we will not discuss in this course.